Drilling is a cutting process that uses a drill bit to cut or enlarge a hole of circular cross-section in solid materials. The drill bit is a rotary cutting tool, often multipoint. The bit is pressed against the workpiece and rotated at rates from hundreds to thousands of revolutions per minute. This forces the cutting edge against the workpiece, cutting off chips from the hole as it is drilled. Exceptionally, specially shaped bits can cut holes of non-circular cross-section. A square cross-section is possible. Process: drilled holes are characterized by their sharp edge on the entrance side and the presence of burrs on the exit side. Also, the inside of the hole usually has helical feed marks. Drilling may affect the mechanical properties of the workpiece by creating low residual stresses around the hole opening and a very thin layer of highly stressed and disturbed material on the newly formed surface. This causes the workpiece to become more susceptible to corrosion at the stressed surface. A finish operation may be done to avoid the corrosion. Zinc plating or any other standard finish operation of 14 to 20 AA micrometer can be done, which helps to avoid any sort of corrosion. For fluted drill bits, any chips are removed via the flutes. Chips may be long spirals or small flakes, depending on the material and process parameters. The type of chips formed can be an indicator of the machinability of the material, with long gummy chips reducing machinability. When possible, drilled holes should be located perpendicular to the workpiece surface. This minimizes the drill bit's tendency to walk, that is, to be deflected, which causes the hole to be misplaced. The higher the length to diameter ratio of the drill bit, the higher the tendency to walk. The tendency to walk is also preempted in various other ways, which include establishing a centering mark or feature before drilling, such as by casting, molding, or forging a mark into the workpiece, center punching, spot drilling, spot facing, which is facing a certain area on a rough casting, or forging to establish, essentially, an island of precisely known surface in a sea of imprecisely known surface. Constraining the position of the drill bit using a drill jig with drill bushings. Surface finish in drilling may range from 32 to 500 microinches. Finish cuts will generate surfaces near 32 microinches, and roughing will be near 500 microinches. Cutting fluid is commonly used to cool the drill bit, increase tool life, increase speeds and feeds, increase the surface finish, and aid in ejecting chips. Application of these fluids is usually done by flooding the workpiece or by applying a spray mist. In deciding which drill to use, it is important to consider the task at hand and evaluate which drill would best accomplish the task. There are a variety of drill styles that each serve a different purpose. The subland drill is capable of drilling more than one diameter. The spade drill is used to drill larger hole sizes. The indexable drill is useful in managing chips. Spot drilling. The purpose of spot drilling is to drill a hole that will act as a guide for drilling the final hole. The hole is only drilled part way into the workpiece because it is only used to guide the beginning of the next drilling process. Center drilling. The purpose of center drilling is to drill a hole that will act as a center of rotation for possible following operations. Center drilling is typically performed using a drill with a special shape, known as a center drill. Deep hole drilling. Deep hole drilling is defined as a hole depth greater than 10 times the diameter of the hole. These types of holes require special equipment to maintain the straightness and tolerances. Other considerations are roundness and surface finish. Deep hole drilling is generally achievable with a few tooling methods, usually gun drilling or BTA drilling. These are differentiated due to the coolant entry method and chip removal method. Using methods such as a rotating tool and counter-rotating workpiece are common techniques to achieve required straightness tolerances. Secondary tooling methods include trepanning, skiving and burnishing, pull boring, or bottle boring. Finally, a new kind of drilling technology is available to face this issue, the vibration drilling. This technology consists in fractionating chips by a small controlled axial vibration of the drill. Therefore, the small chips are easily removed by the flutes of the drill. A high-tech monitoring system is used to control force, torque, vibrations, and acoustic emission. The vibration is considered a major defect in deep hole drilling which can often cause the drill to break. Special coolant is usually used to aid in this type of drilling. Gun drilling. Another type of drilling operation is called gun drilling. This method was originally developed to drill out gun barrels and is used commonly for drilling smaller diameter deep holes. This depth-to-diameter ratio can be even more than 300:1. The key feature of gun drilling is that the bits are self-centering. This is what allows for such deep accurate holes. The bits use a rotary motion similar to a twist drill. However, the bits are designed with bearing pads that slide along the surface of the hole, keeping the drill bit on center. Gun drilling is usually done at high speeds and low feed rates. Trepanning. Trepanning is commonly used for creating larger diameter holes, where a standard drill bit is not feasible or economical. Trepanning removes the desired diameter by cutting out a solid disc similar to the workings of a drafting compass. Trepanning is performed on flat products such as sheet metal, granite, plates, or structural members like I-beams. Trepanning can also be useful to make grooves for inserting seals, such as O-rings. Micra drilling. Micra drilling refers to the drilling of holes less than 0.5 ohm. Drilling of holes at this small diameter presents greater problems since coolant-fed drills cannot be used and high spindle speeds are required. High spindle speeds that exceed 10,000 RPMs also require the use of balanced tool holders. Vibration drilling. The first works on vibration drilling began in the 1950s. The main principle consists in generating axial vibrations or oscillations in addition to the feed movement of the drill so that chips could be fractionated and easily removed from the cutting zone. One can find two main technologies of vibration drilling: self-maintained vibrations systems and forced vibrations systems. Most vibration drilling technologies are still at a research stage. It is the case of the self-maintained vibrations drilling. The eigenfrequency of the tool is used in order to make it naturally vibrate while cutting. Vibrations are self-maintained by a mass spring system included in the tool holder. Other works use a piezoelectric system to generate and control the vibrations. These systems allow high vibration frequencies for small magnitude. They particularly fit drilling of small holes. Finally, vibrations can be generated by mechanical systems. The frequency is given by the combination of the rotation speed and the number of oscillation per rotation. The magnitude is about 0.1 ohm. This last technology is a fully industrial one. Vibration drilling is a favored solution in order to face issues like deep hole drilling, multi-material stacks drilling or dry drilling. Generally, it allows increasing the reliability and the control of the drilling operation. Circle interpolating. Circle interpolating, also known as orbital drilling, is a process for creating holes using machine cutters. Orbital drilling is based on rotating a cutting tool around its own axis and simultaneously about a center axis which is offset from the axis of the cutting tool. The cutting tool can then be moved simultaneously in an axial direction to drill or machine a hole and or combined with an arbitrary sidewards motion to machine an opening or cavity. By adjusting the offset, a cutting tool of a specific diameter can be used to drill holes of different diameters as illustrated. This implies that the cutting tool inventory can be substantially reduced. The term orbital drilling comes from that the cutting tool orbits around the hole center. The mechanically forced, dynamic offset in orbital drilling has several advantages compared to conventional drilling that drastically increases the hole precision. The lower thrust force results in a burr-less hole when drilling in metals. When drilling in composite materials, the problem with delamination is eliminated. Material, drilling in metal. Under normal usage, swarf is carried up and away from the tip of the drill bit by the fluting of the drill bit. The cutting edges produce more chips which continue the movement of the chips outwards from the hole. This is successful until the chips pack too tightly, either because of deeper than normal holes or insufficient backing off. Cutting fluid is sometimes used to ease this problem and to prolong the tool's life by cooling and lubricating the tip and chip flow. Coolant may be introduced via holes through the drill shank, which is common when using a gun drill. When cutting aluminum in particular, Cutting fluid helps ensure a smooth and accurate hole while preventing the metal from grabbing the drill bit in the process of drilling the hole. When cutting brass, another soft metal that can grab the drill bit and causes chatter, the cutting edges of the drill bit, which normally form an acute angle, a face of approximately 1 to 2 mm, can be ground on the cutting edge to create an obtuse angle of 91 to 93 degrees. This prevents chatter, where the drill tears rather than cuts the metal. However, the drill is pushing the metal away. This creates high friction and very hot swarf. For heavy feeds and comparatively deep holes, oil hole drills can be used, with a lubricant pumped to the drill head through a small hole in the bit and flowing out along the fluting. A conventional drill press arrangement can be used in oil hole drilling, but it is more commonly seen in automatic drilling machinery, in which it is the workpiece that rotates rather than the drill bit. In computer numerical control machine tools, a process called Peck Drilling, or interrupted cut drilling, is used to keep swarf from detrimentally building up when drilling deep holes. Peck drilling involves plunging the drill partway through the workpiece, no more than 5 times the diameter of the drill, and then retracting it to the surface. This is repeated until the hole is finished. A modified form of this process, called high-speed peck drilling or chip breaking, only retracts the drill slightly. This process is faster, but is only used in moderately long holes, otherwise it will overheat the drill bit. It is also used when drilling stringy material to break the chips. Drilling in wood being softer than most metals, drilling in wood is considerably easier and faster than drilling in metal. Cutting fluids are not used or needed. The main issue in drilling wood is assuring clean entry and exit holes and preventing burning. Avoiding burning is a question of using sharp bits and the appropriate cutting speed. Drill bits can tear out chips of wood around the top and bottom of the hole, and this is undesirable in fine woodworking applications. The ubiquitous twist drill bits used in metalworking also work well in wood, but they tend to chip wood out at the entry and exit of the hole. In some cases, as in rough holes for carpentry, the quality of the hole does not matter, and a number of bits for fast cutting in wood exist, including spade bits and self-feeding auger bits. Many types of specialized drill bits for boring clean holes in wood have been developed, including brad point bits, Forstner bits and hole saws. Chipping on exit can be minimized by using a piece of wood as backing behind the workpiece, and the same technique is sometimes used to keep the hole entry neat. Holes are easier to start in wood as the drill bit can be accurately positioned by pushing it into the wood and creating a dimple. The bit will thus have little tendency to wander. Others, some materials like plastics as well as other non-metals and some metals, have a tendency to heat up enough to expand, making the hole smaller than desired. Related processes. The following are some related processes that often accompany drilling. Counterbow ringer. This process creates a stepped hole in which a larger diameter follows a smaller diameter partially into a hole. Countersinkinger. This process is similar to counterboring, but the step in the hole is cone-shaped. Boringer. Boring precisely enlarges an already existing hole using a single point cutter. Friction drillinger. Drilling holes using plastic deformation of the subject instead of cutting it. See also, laser drilling. References. External links. Feeds for high-speed drills.